Okay, so hello everyone. My name is Raul Palma. I am head of data analytics and semantics department at Poznan Supercomputing and Networking Center here in Poznan. So I will talk today about this topic of large-scale data integration for getting information insights. Uh, so let me very briefly, before going into our topic of today, briefly describe you a little bit on what is PSNC, because probably some of you haven't heard about our institute. So basically, first of all, we are affiliated to the Institute of Bioorganic Chemistry on the Polish Academy of Science. And we are very well known and renowned organization of research and innovation in Europe, but also an important node in the terms of infrastructure for science in Poland, but also at the European level as well. We collaborate with many different partners around the world. We have, participated in more than 300 projects and coordinated more than 40 of those. So as you can see in our numbers below, some of the main things that we are all involved are related to projects in Horizon Europe and Digital Europe programs, where we are really one of the most active organizations in Poland. So we have like four main locations just for you to see. I mean, we have our headquarters here as a primary centers in Jana Pavła. We have our living labs. We have also a secondary data center, and we have aerospace lab that we have in Konkolevo now. The Just very briefly, our mission can be summarized in three main pillars. One is regarding the digital science, I mean, ensuring the access to cutting edge infrastructure to the research community, where they can, use it as an environment to carry out the research and development. The second one is the digital economy, which is basically based on the research and innovation, creating new results and solutions that can come to the market. And of course, there is a flow there in terms of social innovation between both of them. But we have a very large infrastructure, as I was saying before. Different terms in terms of networking. For example, we run the National Research and Education Network. It's called Pioneer. This is connected to GEAN, which is the European Research and Education Network across the whole European countries. And we are, a member of many different infrastructure projects in Poland, where we have several, nodes across the whole Poland that bring together computing power, storage, and some other infrastructure components into the whole Polish national landscape. This is very briefly our resources here. You can see, we have now more than 7 petaflops of computing power, more than 1,500 nodes, 2 data centers, a lot of storage as well. But one of the important things maybe for you to also see is in terms of quantum, we are one of the most advanced in Poland regarding the, operation of different quantum centers. So, for example, we have been selected across among the 6 sites in Europe to host and operate the first Euro HPC quantum computer. So this is very briefly the fields of applications and the technologies that we are, applying at here at PSNC. So many different types of technologies from big data, HPC, of course, cloud, digitization, virtualization, mobile applications, new user interface, IoT, semantics, and so on. And all of these, of course, as we are a research, but applied research center, meaning that we are really going into different types of sectors, like, for example, education, but also bioeconomy sectors like agriculture, forestry, fishery, but also some others like e-health, cultural heritage, etc. So I hope that this gives you like high level overview of our center, and it's interesting for you to see. Of course, you are welcome to come to our website to see more information. Okay, so let's go now to our topic, which is large scale data integration. Uh, so, as all of us are aware, there is a huge boom in terms of technologies that are available now, like IoT, artificial intelligence, big data, etc. Which, of course, they have been very useful in terms of the possibilities that they bring, but also, because of these new technologies, there has been an explosion of the availability of the data. So there is a lot of data that is being produced by many different types of sources. For example, this one, like, one of our main topics is in agri. There are a lot of different sensors that you could put on the fields, on the in the farm, in the tractors, also some drones that can go through all of the plots of your cultivations, etc., that are generating a lot of data. This, of course, has a lot of potential because this data can be really valuable. But because, based on this data, you can create some kind of smart services, you can create applications that can support the decision making of the different stakeholders. But the problem is that the data that is being generated by many of these platforms and systems normally is not interoperable. So this data normally is produced, and sometimes is even available in data silos that are not cooperating or able to integrate with other kinds of data in order to really turn it into value. So what we are trying to discuss here today is how all of this data that is coming from many different sources can be put together, integrated, but not only like a aggregation of data, but how we can get value of this aggregated data. So here are some nice quotes that the data holds a huge potential for the future of the farms, for example, but only if we can like figure out how to turn this data into a decision, of course. So imagine these challenges in terms of how we can get the value of the data. Uh, this data that is being produced in many different places, many different sources, are talking potentially about the same thing, but there are, describing and talking about this same thing, but in different terms. They talk with different vocabularies, different languages. They don't understand. I mean, the data that is being produced is not understandable between each other. So that means that we cannot really make it together and use it like an integrated way in order to really leverage them. For example, you have here the existing knowledge that is available, and we want to get the value. In the middle, this that you can see in the box, there is a huge gap because, of course, you have the infrastructures where you can carry out many different types of calculations, simulations, analysis, and so on. You have all of these analytics tools, but how to really leverage all the possibilities and the value of these existing data sources in order to give some support in the decision making. It's a huge process that we need to get into more detail. So what is the data integration? The data integration basically is being hampered at the moment because of this, lack of seamless exchange and integration of the data. And this is because we have, this data collected by different systems that really interoperate. Data is available in different formats, represented according to different data models. There is a huge heterogeneity in the semantics used to represent the data. There is a lack of standard used in some domains. I mean, might be some standards available. We will talk a little bit about this, but there is still a lack of adoption of this standard in the use, especially in some domains, right? Uh, and of course, the lack of interoperability mechanisms that allow us to make these connections of the data. So here, these are some landscape that you can see of the different technologies, in health, in agri, in other types of markets. you can see there is a lot of different brands, a lot of different tools, and yeah, there is some big problems in terms of how to make them cooperate. So the data integration at the end will enable these, like enterprises in general, to consolidate and harmonize the data from these different data sources into a unified view. That's more or less the idea here. It's not just about collecting the data, because as I mentioned before, um, you can put the data in the same place, like centralize it, put it in the same storage. But if this is not, expressed in the same language with the same semantics, then we have a big problem, because still we will not be able to really leverage the value of this data. Now, when we are talking about semantics, I'm talking about the meaning of the data. When, for example, I'm saying that this is like the temperature value, this means that I'm talking about what kind of temperature, the air temperature, the seawater temperature. I need to know exactly what is the semantics behind this kind of information that I am, describing. And this is one of the main challenges in terms of making data interoperable and to make the data integrated. So we need to eliminate the data silos. We need to eliminate the duplications, because again, if you have data from different sources, some of this information might be duplicated, and we don't know how to reduce these kind of duplications, and this will lead to inconsistencies later on when we would like to analyze the data. We will, of course, if we put this together in the same kind of language, the same kinds of semantics behind, then we will reduce the errors and we will have a better quality data. So how this kind of data can support the stakeholders in the decision making? So we need, of course, on the one hand, analytics tools, right? So these analytics tools and services that can exploit this integrated data. They will be able, based on this tool, to gain a better understanding on the operations and how, for example, customers, markets are going and moving depending on the results of the data. And based on that, of course, take better decisions, more accurate decisions. So that's the simple idea behind the data integration. There are many different strategies how to do these kind of integration steps in order to get some information insights. On the one hand, you can start with data standardization. Obviously, that includes, the discovery of the data sources, establishing mappings between these data sources with some particular standard. Then is the part of normalization, meaning applying these mappings in order to, represent and describe this data based on this standard. And then finally, validation. So make sure that the data has been represented properly, not only in terms of the standard, but also in terms of the original intended value or intended purpose. There are, of course, strategies based on the ETL, which is extract, transform, and load. So this is a very well-known strategy from many years already. You have, like I said, data, many different data sources. So you extract from these data sources the data, you do some transformation, and then you load into a new place, in a, for example, centralized place. This is the case of data warehousing, for example. So you put everything together in one place, and then you can do analytics on top. There is, of course, also the concept of the data lakes, right? So it's just putting together the collections and aggregation of data, including both non-structured and structured data. So this is a bit different from what data warehousing, because data warehousing, we are typically talking about structured data. But in data lakes, you are also talking about many different types of non-structured data and how to give access to that data. Of course, there is a part of migration possibilities as well. So, when we are coming from old and legacy systems, we need sometimes to do some kind of migration. So the preparation of the data, the transfer, validation, and so on. There is also the strategies of carrying out federations, right? So that means that the data will stay in their original sources, and then we will do some kind of virtualization that just gives you an idea that you are able to access this in an integrated way, but the data is actually, of course, in the original source. So this is also one of the strategies. And Obviously, the implementation of some kind of APIs that will allow then, of course, the extraction of the data and integration with other sources, especially if these APIs are, based on some standards as well. Um, but I would like to go into one of these approaches, which is linked data approach. It's I would say, more innovative approach. It's one of the things that we have been applying and demonstrating in different scenarios, different showcases, how this can really work in terms of providing the possibility to do large scale data harmonization and integration. So the idea here, of course, is linked data. First of all, is a popular method for publishing data on the web. It is used in many cases for data integration and harmonization. Why? Because it has different benefits, like out of the box. First of all, it improves the data accessibility, not only by humans but also by machines, right? So that means that it will be possible to automatize things like the finding, discovery, reuse, the integration of the data, because linked data is in fact based on the concept of integration. So it's really, from out of the box, giving you this possibility of do this kind of links, integration of different sources. So you can, for example, establish connections between different data sets. You can establish data elements, so connect different data elements from different sources to say how these are connected between them, right? So, and because this is based on some semantics behind, then you are able to discover more useful data through those links, doing some kind of inferencing and exploiting the data, for example, of course, with some semantic queries, right? I will take you a little bit more on that in the next slides, but just to give you an idea, at the moment there are over 1.2 thousand data sets with 16,000 links in the what we call the linked open data cloud, right? So this is um, like a international effort to publish data that is in the linked data format and that is accessible through this kind of cloud. So this is the linked open data cloud. There are many large cross-domain data sets available in the linked open data cloud. For example, you have the DBpedia, which is the structured version of Wikipedia, right? So this is also very useful source in terms of connecting to the knowledge that is behind, the Wikipedia and all of these organizations behind Freebase and some other large cross-domain data set. But there are also many data sets in particular domains like life sciences, governments, bioinformatics. So, even agriculture, we are one of the organizations bringing many data sources for the agriculture and fisheries as well, for example. Uh, so, but what is linked data basically? So basically, the linked data is structured data that is interlinked with other data exploiting the semantics. So this is, in terms of how to construct data, is a very simple thing. It's based on a very simple set of principles and technologies. So you have URIs, of course, to identify the things, right? So everything in linked data has a URI. Uh, then you have, of course, protocols, standard protocols like HTTP, and you have technologies and protocols based on the RDF stack. So, of course, RDF as the main exchange format for semantic data. And of course, you have the query language for semantic data that is called SparkQL. So it's actually similar to what you know from the SQL for relational databases, but in terms of the semantic world, this is called SparkQL. So there are many, guidelines already, patterns that give you like step-by-step recipes, how you can publish data using the linked data paradigm uh, that are available. I mean, you can see, for example, the 5-star deployment schema, which tells you how good your data is in terms of the linked data paradigm. For example, if it's discoverable, if it's based on the standard, if it's having links, and so on. So, based on those aspects, you can have like stars. How good is your data? Obviously, like I said, this takes into consideration that data can come from many different types of sources, not only structured data, but also non-structured data. But behind this, all of these concepts, there is a simple building block, which is the triples. So RDF is a directed graph that is composed of triples. In the triples, as I said, of course, you have like three elements. You have the subject, right? That is the thing that you are describing. You have a predicate that means like a field, like a property, relationship, and you have the object, how this is connected to whatever other resource or a value. For example, if it's a property like age, the object in this case will be a numeral, would be your age, right? 20 years, 30 years, whatever. But if it's, of course, a relationship, this object would be, the URI of another element in the graph that is also having its own descriptions and predicates connected to it. So imagine this very simple example, and you have here, the country France. You have a connection to Paris, which is the capital, and of course, there is also a connection. This is the link. The same as is a link establishing with another vocabulary. So this is like when you started to see the connections. Paris and France is coming from the Wikipedia, right? So this is coming from the Wikipedia knowledge, and this is connected via link data to other data sets, very large data set. In this case is the geonames data sets that has information about all of the geo places, like cities, towns, and so on. So you can connect Paris to this same element in this other vocabulary, and in this other vocabulary you have all of this information. For example, what is the latitude, the longitude, the population, etc. So you can see from very simple graph here how you can establish connections between different data sets. And this is like not only applying to linked open data. It's not like everything has to be open in the linked data paradigm. There is something that is called linked data in enterprises, or linked enterprise data, that basically is taking the concepts and the technologies of linked data into the enterprise world. So in this case, the linked enterprise data allows you to create like a unified information space from your business, right? Where you can really start to leverage the value of the existing data. So this is breaking down all of these silos that we were talking before, right? Creating the links between existing data, reducing the complexity of the different sources, and using openness and standardized technologies. Obviously, there is also the possibility to define access control mechanisms to the linked data. So you can, for example, connect the linked data technologies for identity and access management, for example, your key cloak, or you can also establish some basic authentication mechanisms into your technologies behind. For example, one of the main databases and main kind of technologies for storing and managing semantic data. It's virtuoso, but there are many other technologies available which allows you to specify all of these roles and privileges that people can have when accessing the graphs. Important thing is that in the relational world, yes, in the relational world, you have, of course, your tables, you have your rows, columns in the tables, while in the semantic world, when we are talking about the database equivalents, which are the triple stores, You have graphs, right? Like I was saying, because there is, the graph is basically this collection of triples that are representing a data set. So each graph can be a data set. And then, of course, you make connections between these graphs. But you can establish how and who can access to these graphs individually, right? So that's something that is also possible as well. So let's go into the process of this generation of linked data in order to do these integration steps. So of course, you start with the collection of the data. You need to define the semantic informations models that you will use to represent the data that is coming from these heterogeneous sources. Then you establish the mappings. So how to transform from the original sources into, linked data form based on the model previously selected. And then you do the integration. For the integration part, of course, there are two possible roads that can be carried out. On the one hand, there is something that is called the data upgrade of semantic lifting, where take the sources that were probably hidden and not very much accessible. For example, you have a lot of CSVs produced by sensors, whatever, and then this can be lifted semantically to generate RDF data from these sources, and this data is loaded into the some kind of semantic database. I mean the triple store, and then of course you can start to make the connections with other data sets. So then finally you make the publications via some kind of endpoint, and then you put all of the applications on top. But the other route is that you have the sources already there, like it can be your relational database, or it can be like a RESTful endpoint. uh, so then what we can do is to provide some kind of virtualization, as I was also mentioned before. So then in this case, it's going to be some kind of on-the-fly query transformation. So you access the data source as if it would be in a semantic form, while in reality the source is staying where it was, like relational, like API or whatever, but it's exposed as a semantic data. And then this semantic data can also be connected with other data sources. So that's the two main roads. And once you are done with that, of course, you need to provide the access to this integrated data. I mean, you can have different kind of search interfaces for, particularly in the semantic world. We are, having a lot of faceted search interfaces. You have APIs that can provide access to the semantic data as well. And at the end, of course, you have all of these visualization and exploitation tools that can be used to leverage them. So this is something that we call the linked data pipelines here, and you can see how is this reflecting into the big data and AI pipelines, which is based on the VDVA, and the ISO standards that gives you like the main steps in terms of handling the data in these kind of environments. So whatever I was just telling you before. So first on the left side you have the collection. Then you do in many cases some kind of pre-processing. The first line on here in this block is basically the semantic lifting that I was mentioning, while the second arrow is providing you this on-the-fly transformation. But in the semantic lifting, you do various steps: the pre-processing, enrichment, the specification of the mapping, the generation of the RDF data, some kind of post-processing steps, the storage, the linking, and the publication, right? In the on the fly here, you can see you need, of course, a mapping, right? But you don't do any kind of pre-processing and whatever. You directly from the source via the mapping do some linking and publish the data as semantic data. And for all of those, the main source here is this model, the model definition that we have here. Then at the end, on the right side, you can see all the possibilities that you can do once you have the data in this form. So visualization and exploitation tool to do some knowledge discovery, and finally do the decision making support. Uh, so here, just go briefly into the model specification. Basically, behind this is the concept of ontologies that probably you have heard at some point in your life. This is ontologies are like a formal specification of knowledge within a domain, right? So you have here a set of concepts, relationships, how that basically say how the things happen in a particular domain. What are the main concepts in the domain? What are the main relationships in the domain? And this is formalized in an ontology. So generally, when we are doing all of this, process for data integration, the first thing that we need to do is decide this model. Which model are we going to use to represent the data? And here, of course, the main rule is, as always, reuse whenever it's possible, and then just extend as necessary. There are many different vocabularies and ontologies in many different domains that can be used for different purposes. But the most important thing now, when we are talking about these information models, is to enable the interoperability between them. Because, in the past, people were just creating new ontology here, new ontology there, and that's not the purpose of the ontology. The ontology at the end is to have like a common agreed view on of a particular domain. So the idea is now to try to establish the connection between those well-known standard ontologies, so that then data that is available in one, based on one of those ontologies, can interoperate and be integrated with data based on another of those. But that's only possible if we establish the mechanisms for interoperability. So here, for example, this is just very briefly one of the main models that we have been working on the past that is now becoming like a standard for the OGC, this Open Geospatial Consortium, international standardization body. So this is like an approach that tells you into modular and layer architecture, where you can easily extend in the future your model for particular domains. So this particular model, for example, should go into can be adapted and extended to different domains, always reusing whatever is available. This is for one example as well, how later on we connect to standard vocabulary. So there is, for example, essential biodiversity variables. So these are standard vocabulary that people, experts, have come to some kind of agreement. And based on these ontologies, we can connect to these vocabularies and allow this representation of the data based on these vocabularies. So finally, of course, once we have this model, then of course it comes the actual implementation part. So how to carry out the transformation. And for this, obviously, as part of our several R&D and innovation projects, we come with some solutions for that in order to allow you to do this process. Our tooling is coming available as a CLI, as a web service. Of course, we have some RESTful APIs behind as well, user interfaces that allows you to carry out all of this transformation process that I was just mentioning before. So important thing here is, of course, the mapping, because like as I mentioned in the process before, once you have the model, all right, so then the next step is to establish this mapping, how the data from from the sources will be represented according to a particular model. And this is how I'm telling you. So the unit is coming from this particular source. This is a field, for example, in your CSV file or your JSON or your XML, and how this will be represented according to the new model. Based on this mapping, the data is generated doing this kind of very simple interfaces. So you can this is the pipeline interface, so you can generate this data that takes you to the whole steps. At the end, you are able directly to store the data in a semantic database, and then start using the integrated data. But that's not it all. Basically, once you have the data there, as I was saying, there is also a very good important step regarding the specification of APIs, in particular standard APIs, because you have the model that give you the common language. You have the pipelines that allow you to do this harmonization and the integration. But then how to access this data, For other applications, not for users. For user, we will have, of course, our analytical tools, which I will show you in a moment. But for other applications, other services, how to leverage this, ideally we use standardized APIs. And here there is a lot of those standards that are coming from the Open Geospatial Consortium that can be done, to access the data. Here, for example, this is just giving you an idea how once I have harmonized data from many different sources of soil. This is about soil data. How data about soil can be connected to different data sets, and I can, for example, retrieve observations of soil from many different sources in order to give, for example, a particular value of one of the properties that is beyond a particular threshold. So this is like, showing you the capability, and important is that the source is not necessarily, of course, in one place. For example, I'm talking here sources that are from PSNC, sources that are available in the International Soil Institute that is in the Netherlands, and some other in the US. So we are combining all of this data and give accessibility through the API here. But once this is harmonized, of course, you can get also this kind of nice interfaces, right? So you have here LPS data. LPS data is basically information about the parcels of all the different types of parcels that are available in a particular country. And once this is harmonized, you can have data from different countries, in Europe particularly, because each country has its own LPS data. But if we put this harmonized, that's something that we did in one of our projects, is to put all the LPS data from all of these different countries in the same harmonized way. And then you can visualize this in an integrated way. So here, for example, is another way how to get insights. I can see, for example, give me the points of interest that are near some roads that have a particular, type of plot or type of parcel. And this is coming from 3 different sources, and we are able to visualize this data in a simplified way, or to visualize it, of course, on the map, how to group this information from many different sources in a map. Finally, of course, you can do some kind of statistical analysis, like give me, in this case, this is fishery catch records, so fishery data, catch records from Norway. So where, at what time of the day, the catches were more, in which areas they were more, and so on. So you can do analysis of the data based on the integrated data that has been harmonized behind this. And what is the connection of this with the European strategies? So let me give you briefly a little bit on this direction. There is a big focus now in Europe, or what we call the data spaces. So the data spaces, is providing like a single market for the data, right? So basically, it's provide the flow of data between Europe across different sectors, and the European Commission is pushing in the creation of data spaces for different sectors like Green Deal, mobility, finance, agriculture, and some others. We are involved in several of them, and at the end, the data space is a decentralized infrastructure of trustworthy data sharing and exchanging data ecosystem that is based on some common agreed principles. So of course you have behind the infrastructure, connecting different components to pool, access, share the data, all the infrastructure, and to make it fair, and to enforce the data governance mechanisms adhering to the European rules for data, for example, protection of the consumers' data, GDPR, competition law, and so on. But you need to ensure the interoperability and sovereignty. That means the interoperability, the possibility to combine data from different sources, right? And of course, you can get some compensation once you share your data in this space. And this is open to anybody, basically, right? So that's coming from the data warehouses days to data lakes to data spaces. That's more or less how we have been going on. And this gives you an idea of the main blocks behind the creation of data spaces. And many of these blocks are related to data integration, because you have here the models, formats, the APIs, the provenance, all of this information that I was just telling you before is related, to the construction of the data spaces at the end. And the link data actually has been, directly applied as well into the data spaces. So there is something that it's called the link data, real-time link data spaces, right? That takes the possibility to manage and process large-scale distributed sources of streams data, events data into smart environments. This is something similar to what we are doing. Uh, and here are some example use cases: digital twins, risk management mitigation, sustainability of different of production, the life cycle assessment of production processes. These are some cases. Digital twins, for example, is a very nice case that I wanted just to highlight to finalize here, because digital twin is a digital representation of a real world phenomenon, like entities and processes. And this is also one of the main motivations now of the commission. But one of the things here is that the digital twin needs to feed from a wealth of data from many different sources. And again, this data needs to be integrated in order to do this kind of simulation or representation of the real world process and phenomena in a digital world. So we are doing this, for example, in the ocean. We are doing this in agriculture, which at the end will give the possibility to people to make analysis, what if scenarios based on the data that is digitalized and available in the digital twin of the physical world phenomenon. So to sum up, we have here like a large, cloud of different types of sources that are available. The idea here that it can take you different steps in order to get the real value from this data. But based on this value, you can actually create this decision support application, do some analytics to really support the stakeholders into really make more informed decisions in their organization and steps. So that's from my side here. So thank you very much. If you have a question, please let me know. Okay. Okay, so then, I'm happy to, if you are reaching us at PSNC, if you have wanted to follow up on any of these topics. And yeah, so have a good day.